This is dark, and it has huge mass, and it's small. That's three smoking guns right there,
Right.
implicating a supermassive black hole.
In the depths of the universe, hidden at the heart of galaxies, you'll find luminous giants known as supermassive black holes. With a mass of millions to billions of times of the Sun, these massive black holes are known to have existed for 13.8 billion years at the core of each galaxy. But here's a plot twist. If SMBH has been present in the early universe, do they hold all the secrets of the galaxies? What are its origins then? How are they made? The questions are infinite, and so are mysteries. Stay tuned if you want to discover the chaos behind massive black holes' origin. According to research, supermassive black holes are present in nearly every galaxy with a mass around 1,000th of the host galaxy. They are interconnected, which leads them to evolve together, helping to shed light on how galaxies, the major components of the visible universe, came into existence. But here another question arises. Did SMBH exist when the universe was only a billion years old right after the Big Bang? Scientists came up with different hypotheses about the age of supermassive black holes, as it's challenging to evaluate their existence. It is a million times more mass than the Sun, thus how, within such a short period, these massive black holes grow this big? To address this, their identification of location was crucial to evaluate first. The research team chose the Subaru telescope at the top of Mauna Kea, Hawaii, to study the supermassive black holes. But it was beyond challenging than it seemed. The SMBHs have a muted appearance. They don't radiate light or have any shiny properties. Thus, the scientists look for special classes called quasars. Quasars are closely connected with supermassive black holes and help in locating them. As the gas, dust, and other matter fall towards the black hole due to gravity, it results in an accretion disk emitting tremendous amount of light, heat, and radiation, such as X-rays and ultraviolet light, onto supermassive black holes at their centers. These spectral radiations help provide valuable information about the quasar's properties and the characteristics of the supermassive black hole. Quasars emit light as bright as a full moon, making them some of the most luminous objects in the universe. During research, scientists found a wide area glowing 5,000 times the full moon. This discovery led them to pinpoint the presence of 162 quasars in this area. Remarkably, 22 of these quasars are estimated to have existed when the universe was a mere 800 million years old. This large number of quasars also helped the scientists figure out an important concept called the luminosity function. The luminous function simply tells the space density and how early the quasars have been forming in the universe. This function provides strong constraints on all the theoretical models in astrophysics or cosmology that aim to explain supermassive black holes' characteristics and their origins. However, there's another contrary. In the early stages of the universe, it went through a major phase transition called cosmic reionization. The entire intergalactic space was said to be ionized in this transition, but the mystery behind this great ionization chaos remains ambiguous. But while integrating the luminosity function, scientists found out quasars have also contributed to cosmic reionization by only 1%, as they emit exponent 28 photons per second in a unit volume of 1 light year on the side in the early universe. With such a minor contribution, it's evident that other energy sources were also needed to carry out the transition, such as the integrated radiation from massive hot stars forming galaxies or whatever. Despite the quasars hypothesis, the formation of SMBHs in the early universe also led to another theory known as the direct collapse theory. Scientists say that supermassive black holes might come into existence directly under the collapse of massive primordial gas clouds in the early universe. Under suitable conditions, the clouds undergo gravitational collision into a black hole, bypassing the formation of stars, resulting in rapid supermassive proportions. However, The primordial gas cloud also needed to be massive enough to tolerate radiation pressure and resist fragmentation into interstellar bodies. Also, the main challenge to explain this procedure was how those huge clouds can exist and remain stable long enough to support the formation of supermassive black holes. Well, to explain the origin of supermassive black holes, primordial black holes also come into discussion. They are hypothetical black holes that came into existence in the first second after the universe's birth. With masses ranging from 100,000 times less than a paperclip to 100,000 times more than the Sun's, scientists assume these black holes can serve as the seeds for the growth of SMBHs. But this theory also didn't lead to any definitive statement for the origins of supermassive black holes, as their existence is not considered genuine, with limited observational evidence. Additionally, the supermassive black holes, when located in the early universe, had a mass millions and billions of times of the Sun. It created so much fuss about how they could grow this giant in such a short period, right after the Big Bang. Royal University research fellow John Regan once made a statement. It's like seeing a family walking down the street and they have two 6-foot teenagers, but they also have with them a 6-foot-tall toddler. That's a bit of a problem. How did the toddler get so tall? And it's the same for supermassive black holes in the universe. How did they get so massive so quickly? This problem became more perplexed when JWST made a recent discovery of a supermassive black hole in the galaxy Sears 1019. This black hole was smaller than usual, with a mass of 9 million times that of the Sun. What puzzles the scientists more is that it was found right 570 million years after the Big Bang. Then, JWST made two more discoveries of supermassive black holes that existed 1 billion and 1.1 billion years after the Big Bang. The continuous exploration challenges our understanding on how SMBHs are growing this big, but this also puts one confusion to rest, that SMBHs aren't any cosmic rarity. They seem to appear quite frequently in the early universe, which is different from what we previously thought. However, this one idea can help us understand the growth of supermassive black holes. Imagine a baby who's already 3 feet tall at birth. He had a head start, right? Thus, it's easier to understand if he grows to 6 feet quickly. That's how SMBH could begin as large seed black holes and then get even bigger. John Regan also made another analogy about the estimated age of supermassive black holes, saying, if you find a black hole in your garden, you can't know by looking at it. Don't know if it arrived there yesterday, a minute ago, or a billion years ago. It has no history, and there is no fingerprint. So when we look at black holes either today or 13 billion years ago, we have no idea what their age is, so we don't know how long it has been able to grow for. However, he also predicted that JWST and other advanced telescopes might help detect this process. Scientists have launched a laser interferometer space-based antenna, or LISA, a gravitational wave detector that will probably help in this regard. Within the next 5 to 10 years, they expect to have solved this problem. Supermassive black holes also profoundly impact the properties and evolution of the galaxies they inhabit. They significantly influence the galactic structure and their shapes. As they are found at the center of galaxies, the gravitational pull affects the distribution of stars in the core, which results in the formation of a dense region known as a bulge that alters the structure and shape of galaxies. SMBHs can also change the orbit of stars as the interstellar bodies orbit close to supermassive black holes, causing too much tidal force. This can also lead to unique star clusters and asymmetric features in galactic nucleus. However, massive SMBH can also be the result of galaxies merger. When galaxies collide with each other, supermassive black holes also get merged. This process releases gravitational waves and leads to the formation of a more massive SMBH. Mergers also help speed up the burst formation and alter the galactic structure. Numerous research is still ongoing to find out the actual origin of supermassive black holes. Scientists have compiled data from different sources such as gravitational waves, X-rays, and electromagnetic radiation that enable them to portray a comprehensive picture of SMBHs and their surroundings. Researchers have been studying the imprints of cosmic microwave background that provide them a clue about the early formation of supermassive black holes after the Big Bang. However, none of the studies can be stamped as the final statement. As the day passes, technology evolves and helps delve deeper into the supermassive black holes. Till then, let's end the video here. Don't forget to subscribe to our channel and comment below on what you know about the origins of supermassive black holes.